You'd think a rock dropped into the ocean would just plummet to the bottom, right? Gone in a flash. We see it all the time. A stone skips, then sinks. But what if I told you that in the deepest part of our world, a rock doesn't rush? What if its fall is a slow, almost graceful journey that takes hours, not seconds? You think rocks sink fast, but this one doesn't. Our planet is mostly water, and hidden within this vast blue expanse is a place of incredible extremes. Let's travel to the western Pacific Ocean, to a feature that dwarfs even our tallest mountains. This is the Mariana Trench, the deepest known point on Earth. If you could place Mount Everest at its bottom, its peak would still be submerged by over a mile of water. We're talking about a depth of nearly 7 miles, or 11 kilometers. It's a realm of crushing pressure and eternal darkness, a place so remote that it feels alien. And it's here that the simple act of falling becomes something extraordinary. So, let's drop our rock into the water above the trench. Watch closely. It enters with a splash, and for a fleeting moment, it accelerates, pulled down by gravity. But almost immediately, something fights back. The water itself pushes upward, creating a powerful resistance called drag. You can almost see the forces at war. Gravity pulling down, drag pushing up. The faster the rock tries to fall, the stronger the drag becomes. In just a few feet, these two opposing forces equalize, reaching a perfect balance. The rock stops accelerating entirely. It has reached what physicists call terminal velocity. From this point on, its long journey to the bottom will be at a steady, surprisingly slow speed. Why does this happen? Why doesn't the rock just keep getting faster? It all comes down to density and resistance. Water is over 800 times denser than the air we're used to. Imagine trying to run through a swimming pool versus running on a track. The water resists your motion at every step. It's the same for our falling rock. As it moves, it has to push trillions of water molecules out of the way, creating turbulence and friction. This drag force increases dramatically with speed. So, very quickly, the water's resistance grows to a point where it perfectly counters the constant pull of gravity. The forces balance out, and the acceleration stops. The rock is now locked into its terminal velocity, a cosmic speed limit imposed by the ocean itself. Let's put some numbers to this journey. Our average rock, now descending at its terminal velocity, is moving at just about 1.5 feet per second. That's slower than a casual walking pace. So, to travel the 7 miles to the bottom of the Mariana Trench, how long would it take? The clock starts ticking. 1 hour passes. Then 2, 3, 4. It would take our rock nearly 6 hours to complete its fall. Even a much heavier, denser object, like a solid steel sphere, would still take over an hour to reach the bottom. The deep ocean is not an empty void. It's a thick, resisting medium that governs the movement of everything within it. After its hours-long descent through the dark, silent water column, our rock finally comes to rest on the seafloor. It settles softly in the fine sediment, joining a world shaped by immense pressure and slow, deliberate physics. This simple thought experiment reveals a profound truth. The ocean isn't just empty space between the surface and the seabed. It's a powerful, dynamic environment with its own set of rules. It reminds us that even the most familiar laws of physics can manifest in surprising ways in the unexplored corners of our own planet. The deep sea is a world where falling is a journey, not a plunge. Thanks for watching. If you found that as fascinating as I do, consider subscribing for more deep dives into the world of science.